Okay, so on CCLA under week 8, click this link and meet with your groups and discuss when you want to do your final presentation, okay? They're basically just about 1 hour chunks, 50 minutes, okay? The first one will start at kind of 10:10, but after that, everything will just start on the hour, and so, you know, I'll either meet you at 10, 11, I take a break for lunch, 1, 2, 3, 4, or 5, okay? And sign up, okay? Figure out when your group is available, and sign up, and we'll meet that day, okay? And then, and basically what's going to happen is during that time you will you'll meet with me. You'll do a presentation, probably about 7 minutes, 7 to 10 minutes, something around there, okay? And then the rest of the time I will read through your final report, okay? So you got to write up your final report. I will read through it. I will ask questions as I'm reading. You will answer those questions as I'm reading. And I'm going to spend probably, about 40 minutes reading your report and asking questions. And then I will give you a final grade, all right? I think about 40 minutes to read through your report to come up with a grade is a fair amount of time, and I'm going to do that for every group. So it's very time consuming for me, but at least this way, if I've got questions about why you did something or what you did, you know, you're there to answer them, and that's how it will be. Okay. Are there any questions on your scheduled meetings? Okay. All right. So this is week 8. I'll talk SKlearn today, maybe Friday also as well. And then week 9 will be our last kind of week in this classroom. That's next week, and I'll cover SQL, okay, SQL, because I know that's a topic that a lot of you guys are interested in. And really, we only need to spend like 2 days on it, not that much. And then that will be it. That will be it for lectures for the class, okay? So week 10, we won't be meeting at all here, okay? So 3 to 4 o'clock is basically a time slot that you can do a presentation as well. So that's going to be week 10, and then there's no final exam during finals week for this, okay? So you'll do your final presentation during week 10, and that will be it, okay? And so, you know, if as a group you decide you want to go on Monday, you know, just spend, I guess, your Thanksgiving Saturday and Sunday working together, okay? And knock it out, and then the rest of your week 10 is free, right? So anyway, sign up here. I have a feeling most people are going to go, yep, they're already going for Fridays and Thursday, okay. So everybody likes to load the back end, but that's fine. Okay, but I'll be around. Okay, any questions there? I hope you feel like you've learned something in this class, at least regarding the usage of Python for data analysis. So we'll take a look here, okay? Oh wait, is this the right one? Yeah, this is. All right, so today I will take a look at these cross-validation tools. You're gonna have to look at that screen over there. And again, this is stuff within SKlearn. All right, so we load up NumPy, Pandas, Matplotlib. We're also gonna load up SKlearn. We will import our iron slag data. All right, and again, we're just, we want to fit some kind of model here. And we can fit a simple linear regression model, and we've already done this. Okay, and this is where we left off, right? Okay, and so here we did cross-validation. So this is what we did on Monday, and we said this is the thing that we get, and when we do this evaluation, our score is 0.53. So that's our R-squared value. Okay, so as far as the cross-validation score, it's giving us an R-squared value, and we get 0.53. However, when we did actual cross-validation, we see we get a negative 0.086, and over here we get, and then some of the other values we get are 0.49, 0.756, 0.65, 0.412, okay? And I think I told you guys, think about how it's possible that we get a negative value here, right? So normally we think of our R-squared value as kind of the sum of squares model divided by sum of squares total. And I said, is it possible for us to get a negative value? How can we get a negative value? All right, so did anyone figure or think about this? Did anyone give it more than 1 minute of thought? I won't be sad or disappointed if, okay, maybe a little, maybe just the teeniest bit sad or disappointed. Maybe I didn't save that picture. Okay. All right, so we have this. Where's my color palette? This is this, right? That's our regression line. Okay, so this is going to be, this is y bar, and from here to here, this is y minus y bar, okay? And so SS total is the sum of y minus y bar. And then over, I don't know what color should I use here? Here, from here to here, SS error is the sums of each y minus the y hat squared, right? Okay, and then SS model is the sum of y hat minus y bar squared. Okay. So, is it possible? How can we get a negative? How can we get a negative? So we have kind of our so when we look at kind of R squared, we often think of R squared as kind of the proportion of variance explained. Okay, so the proportion of variance explained, this is going to be what? SS model divided by SS total. Is that right? Okay. And we have also said that SS model is going to be SS total minus SS error. Is that okay? So as far as kind of a ANOVA goes. All right. So if we use this, can I get a negative score? So if I say my score can I get a negative score somehow? Maybe, yes? Okay, well, I mean, the computer's saying I got a negative score. So I'm just asking you, how did we get a negative score, right? So why is the computer telling me I get something negative? Because normally if we're doing this, SS model divided by SS total, like here I've got a square, this is always going to be positive, and SS total is always going to be positive. So like, I shouldn't be able to get a negative, but the computer is saying I'm getting a negative, and I'm not saying the computer is always right, but in terms of like SKlearn being this piece of software that has been checked many, many, many times by other people, it's reporting a negative, so it's a good question, like how are we getting this negative thing? Okay, well, what's going on is we're using SS total minus SS error to kind of get this R squared value. So let me just show you, right? So what do we do in cross-validation? How does cross-validation work? So cross-validation says this is kind of your the total data, right? And the total data will get split into different chunks, different folds. So this might be 4-fold cross-validation. And what it says is that these get used to train, and this one will be the validation set. Okay? All right, so let me draw a silly example here. Okay, so let's say you fit a regression model, and let's say these three end up in your training set. So the training will be red, okay, and then and this one in orange will be your validation set. Is that right? Okay, so if we are training only on the red dots, what will my fitted model look like? My fitted model will look probably something like this, right? Do we feel like that seems reasonable? Okay. Whereas if we had no model, where would we fit the line? The line would be kind of the mean of our 4 points, right? So this is, oops. This is y bar, this is no model, okay? And then over here, this is the y hat for the training data. Okay? And so if we look for our training data, okay, if we say, well, how much error is there total? Okay, the total error is the distance from each yi to having no model, right? Just using the mean, okay? And the SS error is I don't know what color I'm supposed to use here. Okay, SS error is this vertical distance from the dot to what the line is predicting, okay? And SS model is how much our prediction changed from using no model. Okay, and so here we can see the SS error for this data point okay, the yi minus y hat is less than y minus y bar, right? So if we look at this, the residual, the red line, is shorter than the distance from the mean. Okay? But let's look at this point in our validation set. What is the residual that we have? Okay, the residual is this distance to the predicted line, right? So if I take this distance, this vertical distance, okay, and then I compare that to just the distance to the having no model, the y bar, what do we see? We see for this point, yi minus y hat, this is the error, is greater than yi minus y bar, okay? So if we talk about the SS error and the SS total, okay? So SS, for this thing, if I square it, okay, which means SS error is greater than SS total. Okay, and so therefore if I do this calculation, if I say my SS model is equal to SS total minus SS error divided by the SS total, this is going to be a negative value. Okay, does that make sense? And what's going on is that you've trained it on these three data points, and so this model fits well for these three data points, but when you throw in your validation point, it's actually performing worse compared to not having used a model at all. Because if you didn't use a model at all, you would have used y bar, okay, for all of the data points. And so the total distance by using a training set that didn't include this point, after you fit it, this distance, it actually does a worse job predicting than not having used a model. Huh? Yeah, oh, I'm sorry, SS, yeah, sorry, SS model over SS total. Yeah, so your R squared. But it's, I guess maybe we'll just call it our score. So I don't know how I should save this. I rarely write anything for 131, so. Okay, so that's what's going on, okay? We're saying that for this validation set, using the model, fitting the model on the training portion of the data creates a model that performs even worse than just using y bar, okay, right? Because if you didn't design any kind of model and just use y bar, that's going to give you kind of your best thing, okay? And so here, this is just a bunch of code. This is not even necessary, but I'll just kind of walk through it, okay? So what it's doing is we're going to take our cross-validation split, and that splits it into training and test values, okay? And it's and so for each one, I'm going to take my take the training values on X, okay? And I'm going to have training X and take the training values for Y, and I've got my training Y. And then I initialize a linear model. I'm going to fit a linear model between the training values x and y. And then I subset and on my test indices, and I create test x, test y. And here what I'm going to do is I'm going to create a scatter plot of the training data in light blue, and the test data points will get green, will be green, right? And what we'll do is we'll plot the line that got fit to the light blue dots, the training data, and we're going to see how it compares to the test data, which is in green, okay? And, to get the sum of squares, we're going to take each of the data points y and subtract off the predictions and square it, okay? And that's going to be kind of our mean squares regression versus the mean squares error, and we'll see what this looks like, okay? And so so this red line is what we fit to the light blue dots here, okay? So you look at this, the red line is fit to the light blue dots, and what this is saying is that, you know what? We are actually better off just having used the green line, which is no model. So this is y bar, okay? Y bar for the green dots is this green line here. And you can see that, especially for these data points down here, they're very close to y bar, right? So if we used no model, we would have gotten like no error here. Whereas when we use the red line, we're getting quite a bit more error, okay? Now, yes, the red line maybe improves some of the fits for some of these dots, but for a lot of these, using the green line is actually better, okay? And so when we calculate kind of the sum of squares from the green line, that's 15.7. If I calculate the total sum of squares to the red line, okay, it's actually even greater, 15.85, right? And so that indicates to us that we're going to get a negative kind of score, our scored value. Okay, in this case, we get improvement, right? So the red line is the line that we fit to the light blue dots, okay? And we can see that by using this thing to predict the values in the green data set, our test data, we actually improve our fit. So if we, so this first line is the squared error from the green line, okay? Kind of the total sum of squares total, and this is the sum of squares from the model, okay? And so the sum of squares from the model is about half of the sum of squares total, and we can see, so we've reduced it by around 49%, and so that's our scored value. Okay, this one does a lot better. Sum of squares from the green line is around 45. Sum of squares from the red line is only 10. Okay, we've reduced it by about 3/4, okay, from around 45 down to 11. Okay, so we've about a 75% reduction, and that's what we see here. Okay, when you do the calculation, you get 0.75, and you can do the calculations for all of these things, and that's how we get these values. So these numbers, we can kind of reverse find them ourselves by fitting the model, okay, and comparing. We fit the model to the training data, and we can compare how much error we get compared to having not used a model at all, okay? And so as far as cross-validation goes, we would want to use it to see, like, okay, is which of these competing models gives us the best performance? And we want to use cross-validation and not just R-squared, because R-squared will always go up as if you make your model more and more complicated, okay? But cross-validation will not necessarily improve if you make your model complicated, because if you overfit your data, your cross-validation will suffer, okay? So here I'm going to fit a quadratic polynomial, okay? Polynomial of degree 2. And so SKlearn allows you to do polynomial features, okay? And so here we're going to do a transform, a fit transform of x, okay? So x right now is just kind of these values 10 through 30, and you can do polynomial features. Okay, so let me just kind of show you what x looks like. X looks like all of these these numbers here, and then poly x, okay, is basically so here we've got 1, 24, and 24 squared is 576. Okay, you got 1, 16. It's 1.6 times 10 to the 1, and 16 squared is 256. Okay, so poly x literally just takes your x variables and we'll create a matrix of values. Okay, one where it's raised to degree 0, raised to degree 1, and raised to degree 2. Okay, or whatever number you want, it'll create an appropriate matrix there, which is useful for us. Okay, this is available under pre-processing polynomial features. You could do this yourself, right? You can just manually do star star 2 to raise them to the second power and things like that. But SKlearn includes some things that just kind of make our life a little bit easier. Okay, and again, if you do SKlearn polynomial features, okay, there's going to be more options here. Okay. As far as you only want kind of the interaction effects and things like that, so it'll output there. Okay, so now we're going to just fit a linear model between x and the x matrix with columns for a constant x and x squared, and then we fit this. We can ask, what is the r squared value? The r squared value does go up from 0.57 to 0.59, but we want to know, okay, does this work better? Okay, so when we did cross-validation, our cross-validation score for linear model was around 0.46. Okay, so what are we going to get when we do it for with cross-validation? Okay, so this is it on the full thing where we haven't done cross-validation. We can say, okay, it fits a little bit better. Our r squared value goes up to around 0.59. When we do cross-validation, our cross-validation also goes up. Okay, it goes up to around 0.50. Okay, versus 0.46. Okay, we go up. Our cross-validation score goes up to around 0.50. Okay, we see that there's still one cross-validation set where we get negative. Okay, where having used the quadratic fit actually doesn't improve versus the using y bar. Okay, and it's because we're still doing the exact same data sets, and so this is just one data set or one validation set that probably by random coincidence these values happen to line up very closely to y bar. Okay, so it's gonna so a lot of times the models that you fit will perform worse than just predicting y bar, because just by coincidence in this data set we've got a lot of points that ended up very close to y bar. Okay, and so so here we're getting kind of negative gains here, but everywhere else we're getting improvements. 0.55, 0.799, which is really good. Okay, 0.71, 0.462. Okay, and so this is just kind of the same plot where I did all of the cross-validation things. Okay. And what I decided to do here is I decided to define, rather than having to copy and paste the code, right? So the rule of thumb is, if you got to copy and paste the code and change the variables, if you're going to do it once, that's fine, okay? If you're going to do it twice, maybe start thinking about writing a function, okay? If you're going to copy and paste 2 times and just change all the variables in one thing and change all the variables in another thing, after 2 times, maybe you should start thinking of a function. The third time you hit copy and paste, definitely write a function, okay? And don't copy and paste and then go through and change all the variables, okay? So by the third time you're doing it, think about, all right, can I replace all of these variable things with some kind of variable in a function and do the exact same thing that I want it to do and do it, right? And so I realized I wanted to do this for different degree polynomials, so I decided to define my own function where I'm going to put in degree, I'm going to I'm going to have the x and the y and the training index and the test index. And so, so I write a function, which is pretty much a copy and paste of what I had up here, okay? So this is just a for loop, okay? And it's pretty much a copy and paste of that for loop, all right? Except, or I'm sorry, not the for loop itself. It's a copy and paste of the contents of that for loop, okay? And then, and here, the only thing I kind of changed was do a polynomial thing with the polynomial features pre-processing, right? Okay, and then so I say, you know, run the for loop on CV split, which, you know, returns kind of that, the tuples of stuff, okay? And I guess a list of tuples, and I call this function that I just defined here, right? And so when I do that, we can see how it performs here, and this is the set that just kind of by random chance we got a whole bunch of green dots that line up very close to y bar, so we actually get negative improvement, okay? But on the other ones, like in this case, the polynomial, the quadratic fit that we did to the blue dots fits our green dots very well, and so we get very good improvement, okay? And we can see that the quadratic fit depends on the light blue dots that appear, right? So if we look at this curve, it looks different from this curve, okay? And that's because the blue dots that we used to train this red curve is different from, you know, these blue dots, right? So if we look at these two things, we can see that the red curves are different, and that's because the blue dots that appeared in our data are different, right? So this one has this blue dot down here, and so it kind of pulls down this edge, but there's no data point down here, and so it's free to kind of start shooting off in the other direction, okay? So we do that, and we get this, all right? And so because I wrote up the function, okay, now my code is a lot easier to do, okay? So so as far as getting all of those plots, it's now just I'm using that one function poly CV that I had defined earlier in the notes, where I'm going to use a third degree polynomial, okay? This part I'm still kind of running the same thing. This is a little bit of copy and paste, but there's only just a couple lines here, right? So here, if I fit a third degree polynomial, my R squared value goes up a tiny bit, okay? And then we can see, okay, well, how does the cross-validation stuff go, okay? And we can see the cross-validation actually goes down to 0.45. It used to, with the quadratic, the cross-validation score was at 0.50, okay? And once we reach cubic, the cross-validation score drops back down to 0.455, okay? And then we can kind of fit all of these things and look at these things, and we can see, you know, for models like this, the fitted thing doesn't do the greatest job, okay? So so we get some issues, right? And so here I've done cross-validation with a fourth degree polynomial, and it drops down quite a bit. My score is now only 0.22, which is a lot worse. I can do all of the plots. Maybe I won't. And if I do a fifth degree polynomial, my cross-validation score ends up being negative 1.35. Okay, that's really bad, right? So because now it's like everything ends up being negative using a fifth degree polynomial. Okay, especially this one. Look at this one. This one was negative 5, right? Saying that I have 500 times more error by using the model. Okay, and so let's take a look at 1, 2, 3, the fourth plot here that we've produced. 1, 2, 3, and we can see, okay, this is what happened when I fit the model on the blue dots. This red line was the fifth order polynomial that it fit, and we can see here's a data point where the fifth order polynomial says we're predicting you're going to be at like negative 25. Okay, but in reality it was at 40. Okay, so this one data point we made a very big mistake. Okay, and so using just having predicted y bar for all of the data points would have been much better than predicting this one data point to be negative 25, right? So we're getting some very serious things, and we can say, okay, a fifth order polynomial, cross-validation tells us the fifth order polynomial is going to be a bad idea. Okay, so anyway, kind of the main feature there, the function that we used here is this using shuffle split to create our cross-validation splits, and then cross-val score to evaluate our model fits. Okay, and again, just like everything else, look up SKlearn cross-validation score. Okay, for more details. Right. Always read the documentation. Okay, always read the documentation. So you can use my notes and stuff as a starting point, but always read the documentation yourself to make sure that you are using the options and arguments that you wanted to use. Okay. All right. So this is the SKlearn basics. That we already covered that. All right. Here's I guess just in the last couple of minutes, I'll just kind of fly through this last example here. Okay. So there's all sorts of different models that SKlearn has, and so one of the things we can use is the naive Bayes classifier. Okay, so the naive Bayes classifier, we're going to use the Gaussian naive Bayes, so it's going to fit basically two independent Gaussian, independent Gaussians product together. All right, and so here is just some arbitrary training data. All right, so I've just taken some data points. This is using kind of there's a function called make blobs. All right, and you can do whatever you want, right? But make blobs will just kind of make blobs exactly what it says it's going to do, right? And so here I've got red data points and blue data points. Okay. And based on this, we want to create a model that will say, all right, if I get a new data point out here, is this a red data point or a blue one, right? If it's like right here, we can be pretty sure it's going to be blue. If it's going to be over here, it's going to be red and stuff like that, right? So here, all we're going to do is we're going to just say, let's use a Gaussian naive Bayes model, okay? And that basically fits multivariate Gaussians that have no covariance. That's the naive part. Okay, the naive part has no covariance to estimate, and so so we go ahead and do that. We just and this is the beauty and danger of SKlearn. There's that all of these models that you want to do, well, all you have to do is just initialize the model, and then you do model fit to the data that you have. Right? You just need to get your data, your x data into a matrix and your y data into a vector, and then you just do model.fit, and boom, sklearn does the rest. And that's like a really nice thing, right? So like in R, if you want to fit like different models, it's like you've got to look up the documentation, and everything works a little bit differently, right? Like you got to import, or you have to load a library for the naive Bayes thing, and you got to read the documentation, and that works differently from loading up KNN, which works differently from k-means and all of this stuff, right? sklearn, it has a very uniform functionality. Even if you don't understand the model, you just say model.fit, and sklearn will do it, okay? But that's also the dangerous part, right? Is that even if you don't understand the model, anybody can type model.fit, and it'll produce something, and maybe it's an appropriate thing to do, maybe it was not appropriate to use that model, right? So always read up a little bit as far as like, should I be using this model in the first place, right? Does it make sense to use a naive Bayes thing? Okay, model.fit. So with a naive Bayes thing, what do we do? Okay, so this is what this is one way to illustrate the how it segregates the space. Okay, So I'm going to just generate a whole bunch of random dots, okay? We're going to generate like 2,000 of them, okay? That's what we're doing. We're going to use RNG for a random number generator, and I'm going to do x new, and we're going to just generate a whole bunch of these random dots, okay? And then I'm going to ask, once I have my model fitted, right? My model is the Gaussian naive Bayes. I'm going to call model.predict on all of these new random dots that I've done. So now that I've got the Gaussian naive Bayes, I can say, make a prediction. Do you think this is red or blue? Now the naive Bayes classifier technically gives back a probability, but if you said like make a prediction, basically it's going to just draw a line at over 50%, and if it's over 50%, it's going to predict it's red or blue or whatever. So we're just going to generate a whole bunch of random dots and say make a prediction for all of these random dots. Okay? And when we plot it, okay, so there's 2,000 random dots, and I put the alpha to be 0.1, okay? So they're light colored, and you can see kind of, basically these dots over here, when we ran it through Gaussian naive Bayes, got predicted to be red, and these ones over here got predicted to be blue, okay? And so this is just kind of a whole bunch of these things. Now, if you don't like kind of this random nature, you could have said, you could have designed a grid, okay, and done a whole grid of points and said, make a prediction for every single one of these things, okay? But again, it's very simple. SKlearn makes everything very simple. You just initialize the model.fit, and then you give it some new data points, and you say model.predict. And then what you do from there is up to you, okay? And that's SKlearn. And again, for your projects, you don't have to use SKlearn. You don't have to make predictions. But if you want to make predictions and if you want to use some kind of machine learning thing, I would say SKlearn is probably the way to go. If you want to do a classical thing like linear regression or ANOVA or even logistic regression and stuff like that, use stats models. Stats models will give you kind of the tools, the classical tools that statisticians like to see in terms of like p-values and test scores and things like that. SKlearn, you can do a linear regression fit, but it doesn't give you any of that information. You might be able to extract the coefficients, but you're not going to get p-values and stuff for each of your coefficients. So those are kind of the different philosophies regarding making models and stuff with Python, and these are just kind of your basic initial tools there. Okay, we'll wrap up there for today. I guess I got a little bit more to cover on Friday. Next week we'll look at SQL, and that will be it. So we'll see you guys then.